this one exceeds the material property, it will continue to grow. The moment I change the crack tip, right, this one becomes big. Alright, the bottom, the curvature becomes big, right? This whole thing drops, the crack will become stable. Alright, so of course you do not want to a situation where you have a part, right, with a lot of crack, then you start to drill many holes, right? Now become a Swiss cheese. So this is a practical example of how you do things. Okay, so this is a simple example of the application of vector mechanics. So coming back to the tutorial, right? If you look at the first question, right, it's really about this simple equation that we are dealing with. So what's the maximum stress that exists at the tip of an internal crack having a radius of curvature and a crack length? So in this question, right, in a very simple way, the most important thing here is okay, a few things. You need to be able to, paint a mental picture of what this question is all about. Over here, 170 megapascal, 170 megapascal. So basically, you are actually pulling it, okay, uniformly with 170. And then over here, I have an internal crack. The key term here is an internal crack. I think you over here for this kind of question, you have to be very careful whether it's an internal crack or not. Internal crack you can draw over here. The moment you draw an internal crack, the first thing you need to do is to make sure that this is actually written as 2A. Okay? So whatever that is given to you, right? First thing is whatever that you apply uniformly will be sigma naught, that will be 170 megapascal. Internal crack 2A, the whole length of the internal crack is equal to 2.5 times 10 to the power of minus 2 mm. 2A, not A. And then the radius of curvature. So how sharp the curvature is, alright, this one, or how small it is given by 2.5 times 10 to the power of minus 4 mm. Once you have this, right, it will be just a simple application of the equation. Okay, so this one you can write 170 times 2, and then times A. A will be 2.5 times 10 minus 2 over 2, because these are 2A, and then over 2.5 times 10 minus 4 mm. For the mm, I do not have to change it to meter because these are on the same units, right? I will be able to cancel out. So you should be able to get a simple answer. Okay? So this is a very simple application. If the question has changed a little bit to say that this is a surface crack of this dimension, then this value will be equal to A. Okay? This is A. Right, surface crack, the length is given by A. Internal crack is 2A. So 2A equal to this value, internal crack. Surface crack, A is equal to this value. So just be very careful. So a lot of students, right, when they get trapped when they're dealing with internal and surface crack. Okay, so just be very careful about it. So this is the convention that we use in the equation. Other than that, this is a very straightforward question. Alright, so this is more of letting you have an implication of idea how this simple idea on the stress amplification on the crack really happens. It's really due to the geometry.
Yes.
And you fall back into the idea of materials, right? Then you realize, right, every time that you deal with a brittle material don't deform. When you crack, right, the tip will always be sharp. So that's why when you have a crack that propagates, right, you always go right through. But when you're dealing with a ductile material, even if you have a sharp tip, alright, the stress amplification factor can be high, and this can actually exceed the yield strength. What you have is a plastic deformation. The plastic deformation can actually blunt the tip. When you blunt the tip, another way of saying this is that they change the geometry of the tip, the curvature can go down. When the curvature goes down, the sigma m value. So for that case, right, ductile material, that's why we say the materials tend to be stable in terms of the crack. Whereas a brittle material, once a crack moves, right, you just go right through. Okay? In other words, if one day you can find a plate, you crack then crack halfway and then stop. Give it to me. I'll give you some reward for that.
1 million
I've never
Toto.
seen before.
1 million Toto.
Then I
Let's
can
go.
use it as an example.
I bring all of you to my showroom. I buy car for you.
This one too high
Alright,
My father shop also bring you all to
I bring you all to showroom. To help me buy my
okay,
car.
so clear on the first one, right?
Huracan
Okay.
Evo.
And because of this, right, I hope you also understand the implication of what you can do.
Go to
Engineering a
buy
quick fix.
$1 million buy.
You need to buy time to extend the life of the component, right? You can just drill one hole at the crack tip. Okay, for that purpose. So just now that article is an example of that. So over here, so drilling holes. Okay. You don't drill hole along the crack, but you have to drill right at the head of the crack. And hopefully this one, after going through the class, you understand without reading all the documents, right, what this bunch of people are trying to do. Okay, the second question is really talking about estimate the theoretical fracture strength of a brittle material is known that fracture occurs by propagation of elliptically shaped surface crack. Okay, so let's go through. Okay. Over here, I just draw again a simple diagram. Over here, what I have is a surface crack. So surface crack length. So this A is equal to 0.25 mm. Okay, I have the curvature that's given by 1.2 times 10 to the minus 3 mm. Okay, when a stress of whatever thing that's applied. So when they talk about stress that's being applied, right, this will be the stress applied, sigma naught. So applied generally throughout, not at the crack tip. You apply on the body of the object. So sigma naught is given by 1200 MPa. So going back to the equation, right? Sigma max equal to sigma naught 2. Alright. You have this one, you have this one, you have this one, you can find this one. So basically, at this particular condition, alright, given all these conditions, when I apply this thing, right, this thing fails. So at this particular point in time, my sigma m here is this particular value that I've calculated. And this is the maximum value that causes the thing to be unstable, and the crack will initiate and go off. So in this case, what you're trying to find is the sigma m at the crack tip. And this happens to be the value where this thing becomes unstable. So this will be your theoretical strength. Alright? Because at this particular juncture, the things fail. Okay, you just imagine I pull, alright, with a stress 100 megapascal, alright, there will be a sigma m. It doesn't pass the material limit. I go to 1,100, nothing happened. 1,150, nothing happened. When I go to 1,200, oh, fail. So at 1,200, the sigma m value, the corresponding value, which is this one, this is the one that exceeds the material properties at the tip. And once it exceeds the one, right, the whole thing will just go. So this is what this machine is trying to say.
Now the formula is A.
Is it okay? Can?
Yes.
Okay, this equation is a very simple equation. A stress amplification is a reference to the applied stress.
The second question is
Okay.
more like, yeah.
Stress amplification is reference to the applied stress times the amplification factor.
Stewardess.
Amplification factor in your mind, right? I think it's very simple. The longer the crack, it should be higher. The sharper the crack, it should be higher. So it will always be A over the curvature. Okay, it can never be the other way around. And then you have a factor 2 and then a rotation. Okay, so this is a simple equation. If question come out in the exam, it will not be given. So
What? Come out in the exam will not be given. So
okay. It's a very simple job in terms of geometry equation. So this one must remember. Okay, question 3 is something that we go into another slightly different topic where we start to talk about fracture toughness. Okay, fracture toughness is a part where we look at here the K1C value. Okay, K. Okay, in the fracture toughness, the way that we deal with this, right, is in a very simple system. Okay. So this K value, to a certain extent, is actually very closely related to the shear and the elastic modulus. Okay, if you look at the way that it's being derived, right, it's something to the idea of this one times your G. Alright, if this is the same thing, E and E is the same, right? Then actually this is actually in the ballpark figure of your elastic modulus. So basically you are trying to find the kind of average equivalent of between the E and G. So this is your actually your measurement of your pressure. So over here there are a few things I just need you to be aware of.
I drank coffee.
A is the same convention that we use, the crack length.
You want you can finish it.
Okay, thanks.
This is applied stress, same thing. Okay. And this one,
Sounds nice.
basically is a shape factor. Okay, this one is dependent on the design of the material. Okay, if you have an odd shape, right, then you have a certain shape factor. So this one you can always read it from, for example, over here, right? Okay, what is your value? What is your y value given a certain geometry? If A over W is 0.3, right? Then your y factor will be something. So it's really related to geometry. This is more of a geometry issue. Okay. So fracture toughness, if you go to fracture toughness, there are a few modes that which we are talking about, the mode 1, the mode 2, and the mode 3. Alright, in this particular course, we are only focusing on mode 1. Okay, mode 1, because this is more of opening up, we are not doing the shearing or the tearing kind of the values.
I finished the final.
Yes. Anything?
Bro, can you explain the part about how K is similar to the modulus?
Okay, can. Anything that I can help there just now?
No, it's okay.
Oh.
They got big mouth.
No.
That's why.
Someone shouting?
Okay, over here, what I meant was, if you look at here, just imagine I have a term. Let's say, similar or whatever. Okay, maybe if I say, okay, let me try a simple example. If I call this a rectangle, this is length and this is breadth, right? Area will be length times breadth. So this is actually in the dimension of the object, right? So this one can actually, for example, this is 10, this is 12. The way that I define the K, right? If you look at the way that I define the K. Okay, just imagine this is the E and this is the G, right? Okay, just now I imagine this E times G, right? E times G. It's the area, right? But the way I define K, right, is the root of this thing. So it actually has a functional form of the dimension. It's not an area. So actually, you look at this value, right? Wherever you get the value, right? If this is actually 10 and this is 12, right? You expect this value to be quite close to 10 or 12, right?
Yes.
Yes.
So to a certain extent, if you try to actually have an idea, oh, this one probably have a functional form that is close to the E or the G value. That's what I was trying to say. It's not an arbitrary term that comes from nowhere. So it's related to the stiffness equivalent idea. Okay? So what I was trying to use the area example, right? Area is equal to length sub length. If, for example, this particular term, right, doesn't have the area equivalent, it actually has a length equivalent function because I actually wrote it over here. So if you look at here, right, if these two numbers are quite similar, you expect your KC to be very similar to your E or your G, right? So that's what I meant. Does it make sense? So a lot of people are trying to understand what is a K and what is actually the composite of the two somewhere in between. Okay, you take the area and then the root. So it's a rectangle, right? If it's a rectangle, right, you are trying to find the square equivalent.
Yes, close to 11.
Okay, so if this is E and G, you times it, right? You are trying to find the K squared, the K times K equivalent. K times K will be equal to E times G. So this one. Okay, this is on the mathematics side. So that's why I say, in terms of the functional form, it's a little bit closer to the stiffness or the shear modulus. Okay, that's a fracture toughness. Okay, so I just try to give a little bit of meaning to the term rather than I just introduce the term without referencing to how people conjure the idea. So fracture toughness is basically E times G.
I saw the SD.
Okay, now back to this particular question.
Oh, there's an LD one.
Okay, over here, I have an aircraft component that's fabricated from an aluminum alloy with a plane strain and fracture toughness. So this one, the K1C, mode 1, it's not I, it's 35 megapascal, and then root M. Fracture results at a stress. This happen. K1C is basically the limit when the thing will fail. Okay, this one, sigma, is actually 250. This is what you apply. When the maximal internal crack, this internal crack, so 2A is equal to 2.0 mm. Okay, so over here, then it says that for the same component and alloy, I think this is the second part of the question. The first part is, based on this, right, if you look into this particular equation, you'll be able to realize that I have this particular term, okay, 35. Okay, I just write the numerical value. I'll not write all the units. Okay, in practice you're supposed to write. I'm just trying to save space here. I have 35, but I do not have the Y. I have the sigma, which is the 250. Alright, I have the root, and then I have the A, right, which is 2.0 over 2. So this is mm. So over here, the only unknown I have is my Y. Correct? So I can find Y, right? For the next question, the next part, right? For the same component and alloy. Whenever you have the same component and alloy, right, even have the same shape, right? They will always have the same Y. Okay? So for the next part, right, the Y is the same, and now you found the Y already, right? They're asking you, will fracture occur at a stress level of 350, where the maximum internal crack is this one. So what you need to do is, you need to find the K value now. Now given the Y, this one you apply here. This one, 325. And then root pi and 1.0 over 2. Okay, so this one you have,
remember you doing math.
Now your job is to find this K value. If this K value, if this one whatever you found right is bigger than K1C, right, you will fail. If this value that you found is less than K1C, it will not fail. So K1C is basically the maximum
TN or
that you should not pass.
TN.
It's a material property
TN and SN, right?
under
Temasek
pressure.
natural gas probability.
So this question really is an application of here. The first part is for you to find the y because both components are the same here. Just trying to give you an arbitrary example.
Then suck in.
Okay, to find your y. This is something that you know, and then later, for example, you have another batch of materials, right? You have a smaller crack, and then you try to load it with a higher. How high or how whether it will fail or not based on the material property. So this is calculation. So based on the calculation, I did not do the calculation. If you have done the calculation, you will find that this value is higher than 35.
Should be
It will
quarters
fail.
if she gives like the surface.
If it's less than 35, it will not fail.
Surfacing all the last few components.
Understand the key steps? I'm more interested in key steps rather than the actual calculation. All clear?
So in exam, if calculation error, so you still give the marks for working, right?
I'll give you a mark for working.
Oh yeah, this case is not test out.
But I know that you will give me the right answer, so I know.
Oh,
Stress you a bit.
I will use this. I will use that one, but if got
You don't have
two
too much
different values,
Yeah.
and
Must stress him to
equation, then I
answer
use
the
the
But if our grade more than 35, then cannot go.
yeah.
Can?
But
So
I
all
find
clear
it
this one?
easier for me.
Simple, right?
But unless got like very complicated, I use.
Okay?
Shigo meditation.
All good, huh?
Perhaps.
So these are actually on a simple crack with something that's inside. So you can always, there are two major equations that you need to deal with. Alright? Just now the stress amplification in terms of stress, how has been bumped up. This one is to test on failure based on material property. So this is also a very simple equation. I expect you to remember.
A equals to y stress square root pi a.
Okay? I expect you to remember. I will not give you this.
Aye.
Was it recorded, right?
Yes, recorded. I need to
Okay,
Doesn't show what he read.
Yeah.
the fourth question
That's
will be
even
another
on
kind of
paper.
failure.
Then sometimes he will switch screen.
Yeah, that's it.
Okay, yes.
Oh.
The fourth question is another failure, and this failure is one of the major problem for a lot of engineering
Downstairs
applications.
coffee got that one.
So if you look at fatigue
Yeah.
failure, right, this is a usual thing that we have always talked about: stress strain, and pull, and then something happen and failure. But in practice, a lot of the things like are all designed well below the use strength.
Yuan Yang.
Okay, it can be operating here,
YUA.
but with time, the thing can
YUA.
still fail way below the use strength. Okay, for most of the practical engineering application, you're operating way below the use strength, but things still fail with time. So this is a non-time zero failure. This is a fatigue failure that actually goes on with time. So in terms of the way that actually we visualize this, right? It's a cyclic SN curve. So you have your stress amplitude and then your number of cycles. So when people try to look at this, right, they always consider this idea that this is maybe your stress amplitude and then these are the cycles. Okay, over here is we try to use a sinusoidal wave. It's just to actually capture the idea that it go up and down, you know, tension, compression, tension, compression. There are a few key terms here. Number one. Alright, this is actually to introduce you to the idea of how does a stress looks like in a cyclic loading situation. Okay, a fatigue failure, right, usually happens on always go tension compression. So fatigue, okay, over here is given that the mean stress, the average value, this is 50 megapascal. Okay, and the stress amplitude is 225. So if I try to draw a sign, what it says here is this is 225. So from the base here, right, the baseline here, okay, to the top will be 225. So if this is 225, right, this one you will be able to figure out what's the value, right? So this should be the sigma max will be 275, right? You are taking Korean class later, right? That's right. This one should be okay, huh? 50 plus 225.
Oh,
You look at this,
你覺得 OK 啊？
Okay.
275.
Cannot mess.
50 plus 225. Can, huh?
50 plus
Nothing
25
nothing
is
magical, huh?
200.
Yeah, 200.
And this one you can find this value, right?
Yeah, you round off to what? Nearest integer?
Yes.
100 nearest.
Yeah.
Nearest 1000 lah. How about that?
1000 is
That's all.
zero eh.
Zero?
So the maximum stress and minimum stress is 275 and minus 175. Okay, so by just having the mean stress and the stress amplitude, you have the mental picture of what is the highest value and what is the intention, and the other one is conversion. This is what you have. Okay. Stress ratio is actually a sigma mean over sigma max. So very simple, you just have to write minus 175 over 275 equal to a value. Notice I put minus 175 over here.
I stuck here.
This will be a negative number. If it's a negative number in integer something, right? You always have two different kinds of stress state, right? One is positive and one is negative. If this thing is a positive number, right? If this is just a positive number, then you know that this whole curve probably is all up or all down. Does it make sense? Okay. So the number also tells you something, and the ratio tells something. If it's exactly 1, you know where is the mean, right?
Yeah, I already okay.
Does it make sense? If they are exactly minus 1, right, you know the mean will be at the 0, right? So it's a very simple idea that people try to actually have this idea. Oh,
I still didn't know.
if I just look at the few key parameters, I know what is the stress all about.
I stuck here.
And then compute the magnitude of stress range. Stress range, right, in a very simplistic term, right, is from this value to this value. You can take the 275 minus this value, or you can just take 2 times of 225, right?
450.
Because up and down, 2 times 225.
Stress
So
range.
450. Does it make sense?
Yes.
All good, huh? So this one should be okay, huh? Stress range,
This is a different method.
okay, 275 minus
Should be cosecant. Then this is a
or
formula apparently.
2 times the amplitude.
Here.
Okay? Very simple.
Integral is.
Oh, secant is.
Okay?
Yeah, correct.
So this one, once you understand how we actually have the mental picture of what this is all about. So this is the important term. This is the stress amplitude.
Actually, wait, no. Okay.
Okay, this one is something people learn from the hard way.
Whoa.
Okay. They realize for materials, right? Different classes of material have a different behavior. So I just want to highlight there are 2 groups. The first one is typically the steel. This one is like aluminium, others. So this one,
What's that? What's maximum minus minimum?
okay, this is your over here, your stress amplitude.
My Spotify rap.
Okay, just in case you forgot what is stress amplitude.
Huh?
The stress amplitude is this value from here.
Yeah, it's a stress
Yeah,
max
the
minus
225.
minimum 1 times V.
Okay, it's not from here to here, the 225 value. So about the mean, basically on each side, right, is 225. So just to give you an example.
Both sides.
The stress is being plotted on the stress amplitude versus the cycle. So in the world of this, right, sometimes they always call this an SN curve.
Oh my god.
You look at here, this is basically a plot where it tells you this part, right,
See,
fail.
and
Fail for this one. So if you ever have a stress amplitude, right, of this value, right, I can use for X number of cycles, and then over here it will fail. Okay, this is for if I use like this particular material. If I go for higher stress, it will fail earlier. Even higher, it will fail. When I go to a very low value, it takes a longer time to fail. So this is for such material, and typically such material are like a material like aluminum. So there's no safe area. But if you start to look at this particular material, right, this one, I try to draw it with a slightly different color, green. If I work on this value at this high stress, it will definitely fail.
Subject want to give me the
If I go over here, it will fail at this cycle. But if I operate below here, it will never fail.
Become 1,000 zero.
Okay. So for this one, it doesn't have the so-called the fatigue limit, so it's safe. So for example, steel, right? If you want to actually design something that you don't want to fail by fatigue failure, you design it so that the stress amplitude is lower than this. Then you will never have fatigue failure. This is what it means. In an aircraft where it's aluminum based, right? No matter how you reduce the stress, you can extend the lifetime, but you will still fail. Okay, so this is a material related issue that you can't get by. Okay, so this is what it means before I actually go into this. So hopefully this is okay. Yeah. So this is an example. Now coming back to this question, right? So I have 1045.
So near your move P plus
0.45 covered, yes. Okay, if a low amplitude, okay, F is applied is 2200 newtons. Okay, calculate the minimum bar diameter. So find the diameter allowed to ensure that fatigue failure will not occur. So if you want fatigue failure not to occur, then you need to make sure that your stress amplitude do not go above here. So your stress amplitude, the max that you can have will be this particular value. So if I look at from the graph, this is something like maybe 310 MPa, right? So this is actually the worst case scenario. Anything above this, you will actually undergo fatigue failure. Anything below, not. And then assume a safety factor of 2. Safety factor of 2 is something I design in to give you that comfort of the basically safety factor. So now if this is the basically max, right? Max equivalent, right? So your design value will be equal to sigma of the max over the factor. So it'll be 310 megapascal over 2.
Oh, hello.
So you have a certain value there. Based on this stress, okay, it's equal to F over A. You have the F times D.
It's fatal.
Fated.
Okay.
I see what's correct.
So basically, the safety factor gives you the margin of error. So if you are very kiasu, you put a bigger number. If you are not so kiasu, put a smaller number. Okay. Military, right? The number is very small. Commercial, right? The number is usually bigger. Especially, I'm using aeroplane as an example. Military planes, right? They want the lightest, fastest, everything, right? They will just push everything to the limits. So the safety factor, there is some safety factor, but the margin of error, they give you a little bit closer because they're pushing to the limit.
G-force.
And I think the most important thing, right? If a military, for example, a fighter jet fail, right? There's still a button that the pilot can press. Aeroplane, right? 777, no button to press.
Oh,
So have to be very safe. Okay, so they design you the factor in much higher.
Imagine the whole top cabin can just
the canopy.
Okay.
I think it's called a canopy.
So these are the safety factors. So
The one
these
that
are
opens,
basically
then
the
can
case.
get
Whatever that you have, you just pull down by the value, you
Yeah.
put at a lower value.
Yeah.
That's what it means.
Like commercial airplane,
But they are trained to parachute, right?
sorry?
Pilots are trained to parachute.
Of course, bro.
As in like
Not
commercial
like
pilot.
die inside cockpit lah.
Yeah.
They never train the passengers to
Is it
This one,
as in
this
common?
one is military, bro.
No, as in
Commercial
com-
die lah.
Commercial? Wait.
You think got so much money put parachute for the commercial pilot lah?
Why not? They're underneath the seat.
Okay.
Then must do for everybody, passenger also.
Let me put, okay, it is, you don't have to worry. I mean, the way they design the plane, I think there are more fighter planes coming down than.
Whoa,
Joshua hear that I think maybe
No,
something
no,
bad
no.
happened to him.
In general, overall, you look at.
You will see him go to the corner there cry already.
No.
Then at the same time say, hey nah, RSCM never sign me on lah. Later he come back home body bag. Try touch wood.
Okay. Let's not go there. I'll just try to introduce you the why is a safety factor. You do not design until the exact point the material will fail.
Single point failure.
So the next question is basically one 12.5 mm diameter cylindrical rod made out of a certain alloy subjected to repeated tension compression along its axis. Compute the maximum and minimum loads that this thing can be applied to yield a particular life of this value 1.0 times 10 to the power 7 cycle. So you are dealing with this particular green line. So the first thing I can do is question number 6. Yeah, you're dealing with something over here. So this is your 2014 T6. So over here, you can go up, right? It's 1 times 10 to the power 7 cycles. This will be your stress amplitude, right? This stress amplitude, you can read some value over here. If I go to 1/7 cycle, if I read up from here, looking at this one, I'm probably looking at about maybe 160 MPa. So this will be my stress amplitude. Okay, compute the maximum loads that can be applied to you. This one. Assume the stress plot on the vertical axis is the amplitude and the data is taken for mean stress 150 MPa. So this thing is done on 150 MPa. So in other words, this is your stress amplitude. What it means is if I want to translate to this is your SN curve, right? This is your SN curve. If I want to try to actually look into the stress over the number of cycles, right? I can convert mentally because it tells me the mean is at 50. Alright? And I know the stress amplitude is 160. This one is 160. So I'll know this value, right? 160 plus 60, 210. This one?
1-1. Negative 1-1.
So this is my sigma max. Sigma min. Okay. So based on this, right, calculate the maximum and minimum loads that we applied. Okay, over here. So basically what you are trying to do is you're finding the load. Load will be F over A, right? Now you have the stress, you'll be able to find. So this is a simple application of a SN curve, and then knowing this, right, then you will figure out, okay, translating from a cycle that is a book value to actually a design. Actually, I cannot do more than, dump X number of load inside the materials. Okay. Okay. Number 7. Okay. At this point, I just want to clarify something. I hope you remember when I talk about brittle fracture. Brittle fracture has this funny kind of you know, if you are the CSI person, it has this idea that it always points towards the origin, something like this, like a chevron. So this will be the source. Okay. So for a brittle fracture always looks like this. Brittle fracture points back to the source. In a fatigue failure, a lot of people, when they look at here, right, they couldn't figure out, is this a fatigue failure or is it a brittle failure, because there are lines. Okay. One simple way to actually remember is, for a fatigue failure, the crack usually open, slowly open. Every time it opens, right, the crack gets bigger. So when you start to see a failure that looks like this, right? You also have lines. Okay? Rather than pointing towards it, right, it's radiating upwards. Okay, can you see the difference between the two? This one points towards the source. This one radiating from the source. Okay, it's just like you throw a stone in the water, right? It just went out. This is fatigue. This one that points back is a brittle. So whenever you have a failed product, right, you take it out and take a look, right? Straight away you'll be able to say something about it already. So understanding the crack morphology, how they go, will let you know which are the failure mode. Okay? So fatigue failure, what really happens is you have a very small, for example, initiation crack. Every time, because of loading cycle, you cause it to open out a little bit, the crack grows a little bit. So when you start to actually look at the micrograph, you realize over here, there are many lines. Okay, the big lines are the beach mark. Yes, I know. Big terrace, or the terrace, the paddy field, the kind of big terrace. If you zoom inside here, you start to see striations, smaller loadings. Also fine lines radiating, same. So over here, right, if you look at this particular picture, the big ones and then the small ones. So if I try to think about this, right, if I try to use as an example, right, when the plane take off, right, if you look at the wings, okay, when the plane take off the wings, that's a major cycle. One, okay, when you land, okay, or take off, that's one major cycle. Maybe you create a beach mark. But during flight, right, where the thing is just have that vibration, those are the ones that create striations. So beach marks are the ones that deal with far bigger loading that cause bigger advancement.
Bro, so the beach mark is a line. Then striation is a lot of lines.
The beach marks are all these big lines. Okay, macroscopic you can see. Striation you have to go with a finer scope, but you still see the same kind of lines. But these small little lines, right, also going in this way, very finer, but they are due to the loading of a smaller load cycle.
How do you spell striation?
It's in the question.
Striation.
Okay, so over here, so some people, right, in certain areas, right, they start to realize that actually if I can do at this, right, they can start to count maybe every one of them, right, is a major loading cycle. It's just like a tree trunk, right? Just by looking at the rings, right, I know how many cycles before I build, or when it started, so they can do a backward calculation. So some people do the counting. So these are more like,
taping?
And why it fails? Okay, so for fatigue failure, right, in a very simplistic term, if you have something here, this whole thing is way below the yield strength. If you start to flow, okay, if you look at this as an axle, right, if you start to flow, if this is already the crack, right, the load bearing area becomes lesser, right? It's the rest of the white area, right? it grows with more and more cycle, right, the load bearing area becomes lesser and lesser. So it's not a time zero failure because over here it's still within your overall use stress limit. But every time that it causes to open, right, the things will more and more likely to fail because the eventual load bearing area is getting lesser and lesser. Okay? So this is the difference. And the four measures are, in a very simplistic terms, right? Fatigue failure for whatever reason, right? Usually do not initiate from center. It's always from the outside. Because you have an object, right? If you try to do tension compression, okay? If I ask you, if I have a beam of this thickness, this is the center axis, right? If I do this, right, up and down, you realize that the distance further away will have the max tension and compression, right? The center will be like a neutral axis, right?
Yes.
Center is that it doesn't flex, right? The outside is always the one that's
Yeah.
the further away you will have more. That's why these are the parts where they are being subjected to more stress. So for those flexing action, right? Usually the crack will not emit from here unless there's a lot of defects.
Yeah.
Okay. So a lot of amplification is happening on the top. So if I have a crack here, if I have a crack here,
Compression, tension, all that shit.
yeah, you flex up and down, right?
Yes.
The central axis will not have a lot, right?
Yes.
It's the outside that has a lot. So if you have a crack that's here,
Good times.
if I have a crack that's outside, right, then that becomes an initiation for my fatigue failure,
After
right?
I did his quiz, actually his paper is
So-
cautious for his.
First and foremost, you need to understand a lot of fatigue failure can come from the surface. So you want to design something that make sure that this do not happen. So how do I make this not happen? The first thing is surface finish. So you want it to be as smooth as possible, right? Nothing rough. Okay. So for example, if you look at Excel, right, everything, right, it tends to be very shiny and well polished. Not because they want it to be nice, a mirror, you know, look at yourself or whatever. It's because they want to actually prevent fatigue failure. The other thing that you can do is because this is something that it can be initiated or during applications, right? If initially you have a very smooth surface finish, but later somebody scratch it, right? Then you also have a crack initiation.
Prevent scratch.
Okay.
Prevent the scratch.
So you want to actually prevent the scratch, and to prevent the scratch, you can do certain thing called hardening. So you can do hardening. You can do hardening by, for example, shot peening. So you by shooting particles to actually cause plastic deformation. So the outside become harder. It's far more difficult to do a scratch later. When people do shot peening, right, is to actually protect. For example, I think I showed you video about the landing gear and all those things, right?
Yes.
Landing gears do subject to fatigue every time,
Correct.
up and down.
Correct.
So it is to protect the surface from accidental scratches. So that's one way. And you can also do, okay, for example, shot peening is one. The other one can be carburizing. Carburizing means what? You put the landing gear or whatever inside a carbon-rich environment, you force diffusion to cause a higher carbon concentration than inside. Outside carbon concentration higher than inside. Higher carbon concentration always harder. So it also protects the thing from fatigue failure. So that's why when you see some of the video as you reflect back, right, on some of the video I've shown, right, when they do those process, high temperature process, actually they are trying to prevent certain things from happening. Okay.
Yes.
Okay. So this one, of course, then the material quality, then you have to buy from the processing, right? Make sure that you buy from a reliable source, right? You buy from those fly-by-night source, right?
So you cheap.
They have a lot of defects inside, then you're in trouble. And maybe the fourth one I can think of is you do not design those with stress concentrators.
Sharp
So
edges.
avoid those sharp corners in your design.
This is what happens if you don't.
Because the moment you have sharp corners, you'll be like almost like a initiation point, and you always the initiation point for failure. Does it make sense?
Yes.
Yes.
Okay, so simple.
Like this.
Okay, maybe go number 9. Give the approximate temperature that creep will happen. Okay, before I go there, maybe easier to talk about creep again, because I think it has creep happens because, okay, just in case you all forgot.
In grain boundary.
Always happens near the grain boundary.
Got this thing.
Okay, the way that I try to explain,
Yes.
I always try to explain this thing in a very simplistic term, right? Creep is basically a movement of atoms, right, to be deposited on the other far end under loading at high temperature. At high temperature,
Just like that. Imagine right, everything point form.
atoms
I don't think it mind.
vibrate more.
I mean, as long as you
point
write
is
valid
there,
points.
If you haven't released the
Sure.
assignment,
Huh?
Easier.
if you haven't released the assignment,
Okay, you vibrate at absolute zero, they are freeze out. When they are melting point, they will move away from each other. But in general, at high temperature, it's still below the melting point, they will vibrate. Diffusion will be easier. But if I compare an atom that is at the grain boundary and an atom that is in the grain, right?
it's like you.
The one at the grain boundary is the one that is not highly coordinated compared to the grain, which means, right,
So the
this one has lesser neighbors. If I want to move, right, I only
unless you
create
see someone then
lesser bonds. So for these reasons, right, the grain boundary, all the atoms at the grain boundary are the preferred one that move. When they move, they leave out with down with
Need
bonds.
someone to stand by.
So if you look at here in the
Green do for you.
picture, right,
Teddy top.
so over here, that's what you see.
You like Teddy top?
Over here, you have a void that's being left by the atom that has migrated away from the grain boundary and deposited. So this is okay. So this only happens at a very high temperature, and typically, all right, we will say that this will be at a temperature that is, you know,
Good time to do that.
going to the range of at least more than 0.4.
Yeah,
The vacuum is scary.
Oh,
The suction.
Because he hit the Teletubby, then I got stuck.
Okay,
oh shit.
so most material will go to 0.4 melting point. So even for example, a steel, have a relatively high melting point, cannot go above
The
0.4
vacuum
because
hit the Teletubby,
you
then I
have
got
creep
stuck.
effect.
Oh yeah.
And that's why we have a super alloy, right?
I saw it.
Can go up to
The ending part, right?
0.8.
I don't remember, but I just remember he hit the Teletubby, then I damn scared. Scared of the vacuum.
Like Formula only, I got see that one something.
Okay, now I just want to quickly touch base on this particular graph. What it
Sailor.
means. Every time that you have a loading, right? A loading. Okay. For example, a turbine blade that's spinning, right? The first time that you apply the load, right, and then the thing extend, right? That is called instantaneous deformation. You have instantaneous deformation, and then you have primary creep and then secondary creep. So this one will extend with a certain time. Okay. So over here, all right, your primary and secondary kind of a deformation is a function of time. If you want to know how long it's extended by, then you have to use the creeps, the strain rate to actually find the overall length. Okay. So this is what you have in terms of the value. Now coming back to that question, right? Okay, so over here, question 9, approximate temperature 0.4. Then you can go for melting point of this one to be able to figure out.
Not kidding.
Four hours.
Okay, for number 10, I will just skip it
Versus six.
because
Just
this one
check.
have to do plotting. I
Must form the
will not do
Singapore
the
then
plotting
run.
here. But let's go to number 11.
So cute.
Okay,
I think it's one of those songs that
for question
I can
11,
agree with Kirin. Very nice.
a specimen of a certain length of a S590 alloy is to be exposed to a tensile strength 80 megapascal. Okay, so 815. So you look at this button plot, right? So this is a stress, and this is a steady state. Creep. Okay. So this is red, huh? There's a certain plot that looks like this. Okay, if this is 815. Okay, it says that exposed to a tensile stress of 80. So if you go at 80 megapascal, you'll be able to figure out the creep rate, right? Okay, the creep rate is how fast it creeps per hour. So, for example, I give you a arbitrary value. If the creep rate is 0.1 per hour, okay, if I use just do maths now. If the creep rate, right, means you always extend with time, right? Because creep is a assumption of time. If I tell you the creep rate is 0.1 per hour, 10 hours, right? What is the creep?
1.
1, right? So the creep rate of the time. So in a very simplistic term, right? Determine the elongation and after 500 hours, assuming the instantaneous and primary creep. So just now when you have that particular picture, you have instantaneous primary, you have a certain value already. So this is a 1.5 mm.
S450.
And then for the steady state one, right? You can find the creep, right? By using the creep rate based on here times 5,000 hours.
Spaceship.
And based on the creep rate, you can actually find the extension. Then the total extension will be this 1.5 mm plus this value. So this part, right, just tells you, this part, okay, just tells you, okay, instantaneous and the primary is 1.5 mm. So what is this particular value that's a function of time? So you just have to times the 5,000 hours and compare to the length. You have the initial length to be able to find.
Huh? Oh, the paper so far.
Okay, so this is pretty much what I want to cover. 12, I'll leave it for you to try yourself.
No. Oh man.
Oh, they say tough.
Okay, that's all I have for today.
Kirin just message me.
General comment on the quiz, right? I'm not too sure whether the quiz, the time is too short or too long, or
Ask me whether can or
So
not.
good.
was 1.5 hours.
Also interview you.
She say okay.
How to do this? So nothing. Interview.
Yeah.
Yeah, he extended.
Yeah, he didn't really give a timing.
Prof, the unit for creep is unitless.
Huh?
The unit for creep.
The what?
The unit for creep.
Creep will be something like a straight.
Also it's dimensional.
Yes.
Okay.
What did they say?
Okay.
Did they say it's hard?
So a general comment, the first two questions where there's more application of phase diagram, the one
Prof, don't give face diagram. So done. Don't face diagram.
Phase transformation.
and then the phase transformation, I think in general,
What else?
quite a lot of confusion.
Mutton side the best.
I want mutton.
Anyway, I'll give you the full solution. The part where I also struggle is when I ask precipitation hardening, right? How do you do precipitation hardening?
You say precipitation heat treatment.
Yeah. So precipitation heat treatment, how will you do it, right? Typically, what are the typical P percent is like a
Heat
solution.
quench age.
Hardening is different. Heat treatment is just the aging.
Aging also can, it's fine with me. As long as you have done part of it, I'm okay.
But,
I'm sharing with you what are the issues that I face.
but I only remember that heat treatment for precipitation hardening only got aging. That's all. In order for precipitate to flow.
Yeah. If you do that, I think I'm also okay.
Ui, I don't
Okay.
know now.
Where my problem starts is,
Yeah,
some of you say heat to the liquid state and then you cool down.
But it's heat at low temperature, right?
Heat to liquid.
Or to dissolve that.
Oh, I just say
You're talking about precipitation heat treatment process.
is it the one in the piece?
Yes.
Yeah.
I just say the sugar saturation.
Actually, quite a number of you say heat to liquid. I was like, wow.
Our assignment.
Jialat.
Bro, but if you mention everything right, it's still okay, right?
Down to the piece.
You mention wrong thing, it's not okay. Cannot mention anything.
But from the last three questions, the weightage same or not? 1, 2, 3, 4, 5, all weightage same, or 1 and 2 specifically higher?
I'm trying to do
Honestly, I
something
can't
about
remember the
this.
answer.
5, 4, 3, 4, 5 higher.
Bro, but if you explain the entire process, cannot be. You heat, then quench, then heat.
Yeah, that one is okay.
Can right?
Yeah, that one is a full. I'm actually expecting that answer,
Oh,
but I'll
yeah,
accept your
yes,
answer.
Come here, I say.
What's the assignment? What's the assignment?
Oh.
What's the
Process of adding solid
He said heating.
Yep.
Cannot.
Okay, maybe
Then I
I
mentioned
just put in
heating,
the
then he say
rest
got
system
problem.
for any kind of
So
phase
you expect
diagram
the
that has
aging
this
part.
Aging part is the
line,
precipitate
right?
forming one.
I have
That's
this
the
one.
hardening already. That's the hardening.
Honestly, just write everything.
Good. I wrote exactly my
If
assignment.
you have anything that's
It's
here,
like the
right,
same thing.
this one you cannot do aging. The first thing that you always have to do is you need to go solution, come back, fix, then you age.
Number
If
one.
you are here, you are here, right? Only alpha plus beta already, right?
Yeah,
You cannot age.
The icebox, right?
It has to be frozen inside. Means it has not come out yet. That's why the full answer should be you have the solution, come back. But I think some of you are confused in the idea of solution,
Every cup is
melt. Draw cup put
both.
So for example over here, I think it's here.
I can do a lot in 15 minutes, you know.
Okay, but some of you say for example become a liquid state. I was
Use your nail lah.
this solid
Trim your nail lah. Then you just take the.
solid solution.
You found the new.
But when I think the solution give people idea that it's liquid.
Siapa got nail? Nasi cut now. They use the sharp.
There are quite a number of you who write liquid. That's why I was. Wow.
Can see.
And then I was trying to wear different classes to really hopefully I can
Oh,
see
what
what
cut?
liquid.
Can see inside already.
I'm trying very hard.
Can see the layer, first layer skin already.
Bob, let's retest
That's how
ah.
deep it is.
Yes.
I'm still reading.
Let's go retest ah.
What the hell?
They start already.
Excuse me?
Yeah.
They start the paper at 8:20.
I may have to wear my mask in the second.
9:20
8:20. They start the paper at 8:20.
But then 9:20 so time finish.
But I hope you understand where I'm coming from.
Where I'm coming from.
Okay, for the exam, alright, the topic will be composites.
Opposites.
Today's one and next week one corrosion.
Yes.
So 3 questions.
Huh?
Shit top.
10 questions.
Oh, no, 3 questions but 3 subparts.
Minimally this.
Bro,
Okay, these 3 topics. Okay, basically these 3 topics.
bro, I think these 3 topics is not sufficient. I don't
Can
pay
set that as maximum also.
No case diagram. No, Bro,
He
no
can't
case
do
diagram.
anything but
Bro,
how to change?
No, he haven't set.
How can not? Final exam paper must already submit by now already. How can do set by now?
Yeah. It's already signed already.
Submitted already. How to change?
Then why you say minimally this thing? Means you can add more.
Can meh?
Yeah.
Yeah,
Whoa.
technically can add more.
This three lying to us ah.
Okay. Oh, shut up. Don't give prof any idea.
Three is a liar.
Between now and 21st, it's a very long time. I can
Shit.
print this on the fly.
All don't talk rubbish ah.
You say something minimally. This confirm you can still add more.
Oh shit.
You can run
But okay, but I hope okay, my point is not to stress you with the test exam, but I just want to make sure that whatever is covered, even if you don't do well, understand where you have gone wrong.
They're both
Repeat
straight.
again.
And that's my
Good lah,
purpose.
same people.
Okay,
Online exam ah.
okay. And I'll try to look at the quiz again and see how I can do something.
Hey, Same the paper, same people. Why don't want?
That will never work.
Okay. So today's
This is
tutorial
still
is
like
more application.
forcing us to buy EV when it's still the
Okay,
same
and then
people. It's just that you're not
corrosion
it's
also a
very
little more
possible at
application.
an earlier stage.
Hopefully can relate.
It's same concept.
Yeah, but this place is not EV.
That one important
No,
because
not in Tesla, BMW is good.
if you go out, right, you see that you have done corrosion. The first thing that you see, some people the wrong thing.
Oh, the new concept car.
Some
Right, change
people.
colour.
That one I haven't seen in Singapore.
Oh, I don't think Singapore will accept that. I don't think they allow it.
The change colour.
Yeah.
Yeah,
Does it make sense?
but it's
You
in
even know this one,
Singapore.
oh, this one galvanic
The car is
corrosion.
in Singapore. 106,800.
Nobody believes this straight away.
Standard model only, haven't spot. BMW.
Bro!
I think the electric cars won't bring more worries. I think the electric cars won't bring more worries.
Yeah, composite. Yeah.
Yeah, the electric cars quite reliable. You can't bring more
Unlike
worries.
Tesla.
Three topics.
Last two topics.
Actually, last time I only tested two topics. I thought the quiz cool because I really limit the scope. Very limited
But
scope.
electric cars, right, they rarely need maintenance.
I mean, yeah, lah. It's still
They are still
maintenance.
need, right? But like, what they 2 years one time, this kind of.
It means you won't follow mileage again.
I don't
Because
know.
no engine. No VTEC turbo. No V6.
For battery, right?
Battery what? Maximum 2 years to change.
As you see the PMD last time, they burn in half fire in the leaf.
That one PMD, that one the capacity. That one they stupid lah.
Same type of battery though. It's all lithium ion. It's just the capacity.
Okay, by next week I'll also print out a set of things that I expect you to do. Equations. I will not give you if what are the equations come up.
Let's say if
Okay, basically all the fractal mechanics one I will not give you. Corrosion one I will give you the nurse equation if I ever come up. The one that with different temperature. The one is far longer.
if y equal to 4, y is the subject, just make y the subject, then you just
KIC don't give the first one, the stress amplification don't give.
it's just like this.
The sigma m don't
It's
give.
just a reminder, it's not really a reason.
Yeah, because the one plus the 4 is already.
Only those two or you have to remember again?
Because sometimes
Those
you
two
exam, you don't know which one comes first.
and yeah,
UFC.
Only those two.
the two.
Then the rest,
The clip one I'll give you.
just try and give me that.
You fight Rion, Rion
Because the one is longer.
Connect McGregor, let's go.
connect.
The rest I didn't clear any.
The clip one is longer. If you look at the
IX3.
maybe okay, this one I don't expect you to remember. This
iPhone come
one,
on.
this one is a little bit more complicated. I will not expect you to remember.
That's master syllabus.
You factorize it and find a home. So keep factoring.
Let me find another one.
Tutorial, the two formulas you need to remember, right?
Yeah, okay, I
If
see.
factorize, then you cannot find home. Use the original one, then just should report.
Easy.
Nani? What?
3 series 252. Used to be 190. What the hell?
That time was 190. Like,
Composites,
Composites.
composites, I will not give you anything. You have to know. All.
5 series 300.
This one, in terms of corrosion, right? This one,
X equal to
this equation,
y.
don't have to remember.
Yes.
Come up, I'll give you.
No, sorry.
So those,
X equal to
you already know, I mean the normal.
you just become.
This one will be given if I ask you.
X
You
equal
won't-
to approaching infinity.
You won't tell which is
But
what
y
is
is just x minus
What?
1.
No,
like that is
basically the
sub-E already,
potential.
already.
You never know, bro.
Yeah, of course. Yeah, of course.
X approaching 0.
If I set this kind of question, I'll definitely give you a table. I don't expect you to remember.
Prof,
Yeah.
the last few slides for this, right?
And
Slide
if
52
I want to
onwards.
find the location of the essence,
There's material selection and the rest. We need to
find x, make f the subject.
No.
Make y equals 0, find x the subject.
I think the key part is the general principles of corrosion control. This one.
So it's just the 11 types of corrosion and corrosion control. That's all.
Yeah, corrosion control.
But I don't know where it intersects.
It says corrosion control, is it?
The sealant.
Y equals to X.
No, actually, if you look at this, right, whatever that is actually coded under the manufacturers tell you, right, when they apply sealant, right, if you look at this corrosion control, under which part? They are actually trying to remove the presence of electrolyte, right?
Ah, yeah.
So actually, whatever they're doing, right, so if you understand the principle behind, then you understand actually corrosion needs to have four things. They are just trying to kill one of those. So you understand the principle of how corrosion happens, right? Then when you look at what they do, right, they paint, whatever, when they paint, what do? Actually, they're preventing the electrolyte from touching. So they are actually breaking the circuit. That's why corrosion can happen.
Okay.
So if you actually start to think through in terms of all the general corrosion and techniques, right? It all boils down to this. If not, then you always be remembering a lot. All those things that you apply, right, is based on this fundamental principle of corrosion.
Wow, this confirm no time to check.
You can actually remove any one of them.
Must check the optical.
Make sense? Okay, that's all I have for today.
Let's go, Guru.
Enter the classroom.
I finished it.
Last week.
He got nobody.
Okay, I ask you a question.
Shit, that's scary.
Or maybe not. You confuse you. You'll have a quick. I give you a moment.
One series,
Okay, so far can understand?
That's insane.
Picture mechanics can understand easy.
Yes.
Prof, what's the question you're gonna ask? You think you're gonna ask something? That's more than my car.
It's just my car plus 20-30k more.
Yeah.
Or close to 40k more. And it's
But damn small.
Intro is intro, literature, everything
Bro, A class only 195.
Nani?
Yeah.
The what spot?
Hatchback.
So the match topic.